For my Choose Your Own Adventure lab, I chose to model the motion of a skydiver. I wanted my lab to be similar to the mass of the black hole lab in nature, in that I would take a specific scenario and, using my Python model, answer a question about the system and/or surroundings. The purpose of my lab was to answer the question, what is the minimum height at which a skydiver can deploy his parachute so that he lands safely? To do so, I took Newton's second law to be the fundamental principle and the skydiver as the system. I made updates to my Lab 2 motion of a falling object model to model the skydiver's motion and used a guess and check method to determine the minimum deployment height. My result was that the minimum deployment height is 211 meters, which is very close to the standard average minimum deployment height of 213 meters. Just as in Lab 2, the two forces acting on the skydiver, which we must take into account, are the weight force, negative mg_j hat, and the drag force. I updated my drag force model to be 0.5 times air density times the drag coefficient times the area of the person times their speed times j hat. I chose this drag model because it has been shown to be accurate in modeling the drag force of a skydiver, where the area of the person is updated to include the area of the parachute once it has been deployed. These two forces added together equal our net force, which we can use in the form of Newton's second law displayed here to update the velocity and consequently the position of the skydiver. For my model, I needed to create a specific scenario. I chose to model the motion of a 55-kilogram person skydiving from 2,000 meters above the surface of the Earth, the average weight and height of a typical skydive. To include the effects of the parachute in my model, I first defined the time the parachute takes to open to be 60 seconds, a statistic I retrieved from the internet, and set the deploy height to be the average minimum safe deploy height of 213 meters. This was to be my starting point. To account for the chute increasing in size and changing shape as it is deployed, I included a drag coefficient rate and chute size rate, both proportional to the deploy time. These formulas were retrieved from the Physics Classroom's article on the physics of skydiving. As mentioned earlier, this lab was based off of Lab 2, which utilized Newton's second law, the drag force, and the weight force to model the motion of a falling object. The scenario of the skydiver is essentially the same as Lab 2, up until the person deploys their parachute. Because of this, I had to break my model up into two parts. In the first part, the diver is in free fall. The drag force increases until it is equal in magnitude to the weight force, and the person reaches terminal velocity. To model this part of the fall, I kept my code exactly the same, setting Fnet equal to the weight force plus the drag force, only updating the drag force to the improved model discussed earlier, and setting the terminating condition of the while loop to be when the diver's position is 0, so we can tell how fast he's going when he reaches the ground. In the second part of the fall, the skydiver deploys their parachute. The effects of the parachute opening are simulated by increasing the size of the person, represented by our ball object, and increasing the drag coefficient, both of which change relatively slowly with time. Inside the main while loop, an if statement was added to begin updating the drag coefficient by the drag coefficient rate defined earlier, and updating the ball's radius by the chute size rate, also defined earlier. These changes are applied while the position of the person is at or below the deploy height, and the time deployed is at or below the deploy time of 60 seconds. All of these changes affect the drag force, as will be seen in our model. Running the code, we see that initially the only force acting on the diver is the weight force, represented by the yellow arrow, which is constant throughout the entire fall. The drag force, represented by the blue arrow, increases until it is equal in magnitude with the weight force. At this point, the diver has reached his terminal velocity. This checks out with our earlier predictions. When the diver has reached the preset deployment height, we see a drastic increase in the drag force, and the size of the ball begins to increase proportionally to the increase in the size of the parachute. While the drag force is larger than the weight force, the diver's downward velocity slows drastically until he reaches the ground. These observations also check out with our predictions for the second phase of the diver's fall. The speed printed out on the Python shell is 4.9 meters per second. This is just below the safe landing speed of 5 meters per second. Decreasing the deployment height below this height resulted in a landing speed above 5 meters per second, so I settled on the 211 meters. Looking at the graph of the velocity versus time, we see that as expected, the diver's velocity increases until terminal velocity is reached, where the slope of the graph is a constant horizontal line at negative 33.84 meters per second. We can clearly see where the parachute is deployed, where there is a drastic decrease in downward velocity that tapers off towards the end where the drag force decreases. The minimum safe deployment height I determined was 211 meters, only 2 meters off from the 213 meter average safe deployment height. As this height can be affected by weight and the dive height, and my calculation was specific to my scenario, I would consider my lab to have been a success. In conclusion, by applying Newton's second law, the drag force, and the weight force to a two-phase Python model, I was able to accurately model the motion of a 55-kilogram skydiver falling from 2,000 meters. From this, I was able to use trial and error for the parachute deployment height to get the landing speed just under the 5 meters per second safe landing speed.